just some more college physics, and I'm going to do some problems, or a problem, involving resistors in series and parallel combined configuration. So, we know how to add in series straight across. We know how to add in parallel, inverse of the sum of the inverses. What we want to be able to do is break down a system, figure out what the overall equivalent resistance is, and then utilize that breakdown to build back up and figure out what are the individual currents and potential differences through and across each resistor in the given system to begin with. All right, so let us just go ahead and look at the problem. Pretty basic one, but here it is. All right, so we've got ourselves a system here. We've got ourselves 4 resistors with varying resistances. We've got an R1 is equal to 100 ohms, R2 is equal to 200 ohms, R3 is equal to 300 ohms, and R4 is equal to 400 ohms. And we're going to go ahead and say we've got a source potential here, and let's just call that that's 20 volts. And then we know, we want to know what does the circuit look like? Well, we need to know the configuration. So we go ahead and draw something out here. Let's take our configuration to go R1. What's going on? That's not how I like to draw it. I'm going to do it R1, R2, R3, R4, source potential. All right, so there we go. We've got our 4 resistors there, and part A just says, what's the equivalent resistance of the entire system here? REQ is equal to what? All right, so what do? We just start collapsing this down until we got one resistor. So again, what do we need to do? Identify what is just in series or what is just in parallel. So we look at this and say, what can we see here? Where would be a good place to start? And really for this, there's only one place. 2, 3, they're in series with one another. Let's make another resistor out of R2 and R3 by putting them together into one and call that R23. So we'll just go ahead and do that. Draw a little, hey, this circuit's gonna now look like this. Getting messy. There we go. So that's our R1. That is our R4. Our R4. And we got ourselves R23 right there. Or R23. R23 is R2 and R3 in series. What do we know about series? We know that they just add straight across, right? R23 is then going to be equal to R2 plus R3, which will be equal then to 500 ohms. Fantastic. There we go, got the same source potential here. Then we go to the next step. Put it on over here. This is going to get smaller here. So now what do you want to do? Do you look for something that's just in parallel or just in series? And we've got this section right here. Those two are in parallel with one another. Let's collapse those down. So we'll just go ahead and do that. We're going to have ourselves R1, and then those two that were in parallel, they come down to form one branch. And we've got this. R1, now R2, 3, 4. Or R2, 3, 4 is R2, 3, and R4 added in parallel. R2, 3, 4 is R2, 3, and R4 in parallel. So what does that mean? Well, it means that R2, 3, 4 is going to be equal to 1 over R2, 3 plus 1 over R4 quantity to the negative 1. All right, so what does that equal? We got 1 over 500 plus 1 over 400. We can start doing common denominator. 24, 9 20 is 29ths. All right, let's just do this. I've got 1 divided by 500 plus 1 divided by 400 minus negative 1. What's going on? Delete, 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 delete. I don't know what went on there. 222. So we've got R2, 3, 4 is equal to 222.22 ohms. There we go. So what's next? I'm just going to drop this down here. So now we're just going to take R1, add it together with R2, 3, 4, and we've got ourselves REQ. So from here, we've got ourselves the source potential, and then we've got REQ, which is going to be equal to those two added in series. Hey, they're in series, they just add straight across. We've got R1 plus R2, 3, 4, which will then be 100 plus 222.22, which will be 322.22 ohms. All right, so we've got ourselves the first answer here, 322.22 ohms. 322.22 ohms. All right, so what do we do from here? Well, we go on and answer part B, which is what is the potential difference across and the current through each resistor in the original package there, in the original circuit. So what do we have with this? Well, we can kind of draw something out here. Drawing the conventional current comes. We've got ourselves some I1 here. I1 comes in and splits off into, I'm going to call this I4. And well, we've got this. We've got an I2 and an I3. I2, I3, but they have to be equal to each other, right? Because those are on the same branch there. So that's something that we can kind of get, is that I2 has to be equal to I3. So we could call it either. We've got an I4 goes through resistor number 4, I1 goes through resistor number 1. And we just start back here, figuring this stuff out so that we can figure out what all those values there are. So, as is often the case, a nice little table of quantities is helpful just to keep track of things. This one's not that bad because it's only 4 resistors, but it's just good practice to keep things organized. Have all your different resistors. We've got an R1, we've got an R2, we've got an R3, we've got an R4. And we can start looking at sort of the interim ones. We got an R23, we got an R234, and an REQ. R23, R234, and an REQ. And we know what all these values are. I'm just going to write them down. 100 ohms, 200 ohms, 300 ohms, 400 ohms. This was our 500 ohms, R23, 500 ohms, R234, 222.22 ohms, and then REQ, 322.22 ohms. So we got all those resistances. What else do we need to get then? We need to get the currents and the potential differences until we've got these 4 here. And that's going to come with the last steps. So, put currents in one, put potential differences in another, and kind of go from there. So let's just go ahead and start crunching that up, shall we? Start with this, the simplest circuit that we have. 1 resistor, hooked up to the source potential. What do we have? Well, we've got the definition of its resistance. Let me do purple here. And we can say that Req is going to be defined by the source potential, because that will be the potential difference across its terminals, divided by the total current. There we go. What can we do with that? Well, if we know what the source potential is, that was equal to 20 volts. So we can go ahead and get what the total current in the circuit is. I total is equal to Req, excuse me, source potential divided by Req, which will be 20 volts divided by 322.22 ohms, which gives us that I total is equal to do it. 322.22. All right, I got it. We get 0.62069. Let's call that 62.07 milliamps. 62.07 milliamps. I'm going to write it in milliamps. Commonly, we'll do that in milli 10 to the negative 3. So we move that over, we'd have 0.06207 amps. But again, I'm going to write it in milliamps. So we've got I total, and we've got the source potential, 62.07 milliamps, and the source potential, the potential difference across that particular resistor, 20 volts. All right, so then we move on from there. We say, okay, we know everything about this system. We want to then go over to this system and say, what can we figure out about that? So we take this resistor, Req, and we break it apart into R1 and R234, and ask now, what's the current through R1 and R234, and what is the potential difference across those two resistors? So what we rely on now is the rules for series and the rules for parallel pertaining to either how potential differences get split up or that they're the same, and how currents get split up or that they're the same. This is one singular branch. Hey, this is still one singular branch. All we did was pull this apart into two. Does that change the current through the individual resistors? No, it's the same singular branch. Current has to be the same everywhere in a branch. So we have that I1 is equal to I234 is equal to I total. So we've got an I1, I234, they have to be equal. And thus, I1 is equal to I234 is equal to I total, which is then equal to 62.07 milliamps. All right, so we know the potential, we know the current through R234 and through R1. If we just want to know about R1, we're done, but we want to know more than that. Anyways, we've got I1, 62.07 milliamps, and we've got R234. So we've got I234, 62.07 milliamps. And that then allows us to go ahead and determine what the potential differences are across those individual resistors, because we just go back to the definition of those individual resistors. We've got that R1 is defined as a delta V1 divided by I1, which we can then say delta V1 is equal to R1 I1, which is equal to 100 ohms multiplied by 0.06207 amps, which all we're going to do is move the decimal place over twice because it's just multiplied by 100, and we get delta V1 is going to be equal to 6.207 volts. Pretty straightforward, right? We do the same thing here for R234. Why not? R234 is equal to delta V234 divided by I234, which then gives us delta V 234 is going to be equal to R234 times I234, R234 222.22 ohms multiplied by 0.06207 amps. Calculate that out, and without even calculating it, I'm just going to go out on a limb and say, that should be about 13.793. 13.793. That sounds right. Do the calculation in my head really quick. Let me make sure. So we got 222.22 times 0.06207. 13.793. That's what I said, huh? 13.793? How did I calculate that in my head so quick? You say, you memorized it. You memorized it. And I said, no, I didn't. I just made this problem up. A little variation of something that I normally do, but this is different numbers. So we get ourselves delta V 234 is equal to 13.793 volts. How did I get that? The potential difference gets split up amongst those two, right? The potential difference across this was 20 volts. Now it's split up amongst R1 and R234. So the potential difference, delta V1, plus the potential difference, delta V234, has to add up to be 20 volts. What's 20 minus this? Whoosh, this. Or we calculate it out using that, that's fine too. But that's how I got the answer. Anyways, we proceed onward from there. We know everything about that circuit now. We're getting to the good stuff here. We'll come on over to this one here and say, well, what do we got now? Well, we've got that R234 is going to be pulled apart into R23 and R4. What do we know it's the same? Potential differences, right? Parallel potential differences are the same. So we have delta V4 is equal to delta V23, which is going to be equal to potential difference of which they're composed. We're pulling them apart from this, so that has to be equal to delta V234, which we know now to be 13.793 volts. Great, we know the potential differences across those two. So we got a R4, a delta V4, 13.793 volts, and a 2.3, correct? Yes, 2.3, a delta V2.3, 13.793 volts, which then allows us to go ahead and get the currents, right? So by utilizing definitions or Ohm's law, really, we can go ahead and say that I4 must be equal to delta V4 divided by R4, which will then be equal to 13.793 volts divided by 400 ohms. So we'll go ahead and get that one. 13.793 divided by 400 gives us 34.483 milliamps. 34.483 milliamps. 34.483 milliamps, and that is I4. And we've also got I23, which should be what adds up to give us this. So it looks like that's going to be like 27 point something, but we'll calculate it out. We've got I23 is equal to delta V23 divided by R23, which is then 13.793 volts, divided by R23, which was 500 ohms. 13.793 divided by 500 gives us the 27.586 milliamps. 27.586 milliamps, such that the current through I4 plus the current through I23, or R23, ends up being the total current that was through R234, of which those two were composed. All right, we're almost there. What's left to do? R2, R3, and that is done specifically by taking this taking R23, pointing it apart into those two resistors right there. We already know that I2 is equal to I3, so you got I2 is equal to I3. They're on the same path. They are in series, and that must be equal to I23, which was our 27.586 milliamps. 27.586 milliamps. What's left? Hey, figure out what the potential differences are then. We've got delta V2 is going to be equal to I2 R2. R2 is 200 ohms. I2 is 0.027586 times 200. We get ourselves 5.5172. 5.5172 volts, and delta V3 is going to be I3 R3. I3 is 300, excuse me, R3 is 300 ohms. I3 is the same thing, so we've got 300 times 0.027586 gives us 8.2758. 8.2758 volts. What happens when we add those two together? We got 13.793. Oh, that sounds familiar, 13.793. That makes pretty good sense, actually, because the potential difference gets split up across those two. So in the end, we've got ourselves delta V2, delta V3 is equal to 5.5172, 5.5172 volts, and 8.2758 volts respectively, with current of 27.586 milliamps, 27.586 milliamps. That's I2, that's I3, everything about everything. Last thing that we could ask, what's the total power that is supplied to this network of resistors? And just like with capacitors, we can use equivalent resistance. Say P total power supplied is going to be equal to I total squared times Req. Or we could add up the individual current squared times the individual resistors, and this right here for the main thing, but this is a little bit easier, right? I total is going to be equal to, what is I total? It was 62.07 milliamps, so we got 0.06207 amps quantity squared multiplied by Req, which was 322.22 ohms, gives us 322.22 times the quantity of 0.06207, 6207 squared. 1.241. 1.241 what? Watts. 1.241 joules per second is how much energy this system utilizes in terms of the resistors taking energy away. All right, good stuff. Same sort of scenarios as we had as capacitors, now with resistors. Be well, have a good day. Until next, take care.